So this is an official start.
Yes.
Hello, everyone. Welcome to module 3 of our online lecture series on health inequalities. And today we are going to have a double session. In the first session, we are going to listen to Auke Rijpma from the Research Institute for History and Art History from Utrecht University. And in the second session, Myra Morkens will continue. And the first session will be on the OLS regressions, models and causal differences, or as you can see here for OLS for the demographic historian. So Auke, the floor is yours. Thank you.
All right, thank you so much. And yeah, as you can see, I'm sort of flexible with titles and stuff. And as will become clear in a bit, I've sort of tried to tailor this to what I think you, the audience, assuming you're all sort of demographic historians or at least interested in that topic, might in particular find interesting. I figured I would first just say something about myself. And I'm still contemplating whether we should do like very quick introductions of who's in the audience. But then again, we don't have a lot of time, so maybe that's not the best idea. I'll first say something about myself, right? I think that's only fair that I'm not just a talking voice. So as the introduction already said, I'm Auke Rijpma. I work at Utrecht University, and I think I'm maybe a bit of an outlier in the whole lecture series, in the sense that I think that there are just lots of demographic historians, right? People who properly specialize in studying fertility, mortality in particular. Yeah. I'm slightly different. I think I'm an economic and social historian by training, and I think I've sort of being a very data and quantitative oriented person, have always had a very strong interest in what goes on in the field of demographic history. But sort of my background as a training is a bit different, because I'm sort of more looking at what's going on in economics. That's just what our field does, rather than what happens in demographics, which I think is primarily what the demographic historians I'm talking about do. So that out of the way, right? So my main interest is the long run development of welfare, right? So how have living standards improved over the past centuries? How does that relate to economic growth? These sorts of questions. I tend to take a very data intensive and quantitative approach to these topics, and that's also why I said that I think I end up looking quite a lot at what goes on in the field of demographic history, because of course things like mortality, disease burdens, these sort of things are also a very important part of welfare, and of course the demographic historians, all of you, also take your data and your methods very serious. So it's hard not to look over the fence. Okay, so I think I am gonna skip the bit where I ask all of you to briefly introduce yourself as well, right? I think simply for the sake of time, as we'll see, I'm going to try and cover quite some ground. That said, though, I don't think you should interpret that as a lack of interest in what you might think at any stage, or if you have any questions, right? I don't want it to just be one-way traffic. I think at any time, if you have a question or a comment, don't hesitate to interrupt and ask, and I think that will make it more interesting. All right. So if you saw me just test my slides, I am. Oh wait, that comes up next. All right. So a bit of an introduction, namely who this is for. I think I'm going to try and do two strange things at the same time. I'm both at the same time going to try and give a very general and gentle introduction to OLS models. So basically, what's going on here. I think quite a lot of what you'll find in here you might also find in an undergrad statistics class about the topic. But at the same time, I'm also going to talk about what I think are some of the most popular and important extensions of the OLS model, namely those addressing issues of causal inference in applied research, right? So that's two things which can be pretty far apart. But my motivation for doing that is that I sort of assumed there would be a bit of a mix of two people, sort of really young scholars, maybe someone doing a research master's or starting a PhD, and maybe you had some, but not a lot of statistics in your undergrads. But applying OLS in your research is maybe still something you don't have a lot of experience in. I can also imagine there's quite a lot of you who are maybe slightly more seasoned demographic historians, right? So you've been working on your PhD for a while, maybe you're a postdoc. And sort of my cliche of a demographic historian, which will come up in a bit, all in good spirit, is that the survival model is an incredibly important workhorse model here. And that OLS just isn't used quite as often, but maybe you're interested in what to sort of use a Dutch expression, the grass in the neighbor's yard, which is always greener. So to see if maybe there's interesting stuff going on there. I'm sort of assuming we're all kind of familiar with basic statistical concepts like a population and a sample, these sort of things. But at the same time, I am not going to go into huge depths. Okay, and so as you already saw, there was gonna come a meme. Because I like to have at least one or two memes per lecture. And this is basically a memory of me co-authoring something with a proper demographic historian. And every time we had these discussions, why weren't we estimating a survival model? And this, of course, from The Simpsons, when Fat Tony wants his money and explains that his wife, and in this case the co-author, wants survival models. And basically, demographic historians really like survival models. And when I share the slides, right, we also have a slide mocking economists. Basically, them thinking this is another meme. You should just click it. It's a complete classic. I like to think. Basically, mocking economists for using nothing but OLS models. Right, and so that's kind of where I'm coming from here, right? That there are sort of slightly separate traditions, and that maybe what the other one is doing can be interesting. Okay, so very concretely, right? I think we're almost about to really start. What we will actually cover, right? So basically, a very basic introduction to what the OLS model is, some key concepts, how you interpret these models. And we're also going to look at estimating them in R, in particular using a library that I really like a lot. I'll explain why as well in a bit as well, which is called the fixest library, right? And like I said, we'll skip over a lot of details, but I do hope it sort of shows you, if you're not very familiar with these models, basically what's going on and how you can get a basic estimate on your screen. And then we're actually going to skip over a lot of stuff that would be covered if you just follow lots of these courses at university, and we go straight to the big question of causal inference. Mainly because I think that's where sort of why these models are still incredibly popular in applied research, because they're very useful to this end. And here we really can't dive into the details. That could be weeks and weeks of lecture material. But I do want to show why they're so important and what sort of the basic intuition is between some of them. And then what I would really love is that maybe you walk away from this lecture thinking, hey, actually this kind of model might be very interesting for me. And then, of course, there's the internet, there's your university, there's no shortage of resources to really follow up at that. We're going to look at the estimation of one of these models, differences at the end as well, how you do this in R. Hopefully, because of course we don't have forever. Okay. So let's talk a bit about the OLS model. So I'm going to use, by the way, regression analysis and OLS completely interchangeably here, because Yeah, that's how much it's the default for where I come from, right? So it's, I would say, the workhorse of the social sciences. It's very hard to imagine sort of fields like sociology or economics if you somehow did not have OLS. And well, to keep it sort of very vague, we're going to make things lots more specific in a bit, right? What it can do is quantify the strength of the relationship between variables. And as I think many of you will also probably already be familiar with, you can do this possibly in a way that sort of keeps other variables constant, which we'll explain is a very useful thing. And the nice thing about OLS, and like I said, things will become way more specific, but I thought I'd give it in a nutshell to start with, is that the results of an OLS model can be interpreted as so-called marginal effects, namely the change in one variable, the predictor or independent variable, which will always be denoted with an X, a 1 point increase in that variable on the outcome variable of interest, which will always be Y. And of course, we can also perform statistical inference on the results to account for uncertainty. And that's, again, something, of course, which is very desirable. Okay, so a few more things before we really start looking at some details, right? So what are some of the advantages of the OLS model, right? I'm gonna skip over the disadvantages largely. I'm just going to try and sell it to you. I would say it is an extremely flexible method, right? So lots of models you might want to estimate can, with a little work, be written as an OLS model. And actually, there's also in R, it's nice, sort of fun to look at rather than really important. Also, a special library which sort of basically uses OLS models to replace something like 6, 7 statistical tests you might do, things like t-tests and ANOVA tests. You can all basically rewrite them as an OLS model, which is nice because it means if you understand one type of model very well, you can actually do a lot of your statistics in just one well-understood model. And as I already alluded to, and as we'll return to sort of at the last 15 minutes of the lecture, right, there are many important extensions to the OLS model, right? So that's about clustered research designs, like individuals living in municipalities, these sorts of things, and those causal inference strategies I've mentioned, right? We'll return to them, so I'm not going to list them right now, but you've had a first quick look at them. I would say many of these advantages that I mentioned can also be estimated in a non-OLS context, right? So that could be like logic models, logistic regression, or those survival models I keep sort of talking about as the big other thing. But I would say for many of these things, you will find that methods come to OLS first because it's just in its core relatively simple. Whatever extension you have in mind will be pretty complete and will come with a good package. So that's been recently updated, is complete and well documented. Whereas if you try to extend a slightly more complicated model in one of the ways we'll describe, you'll sort of run into the annoying fact that you're sort of at the research frontier of statistics, and that will sort of limit you here. Okay, this will be the very last thing I say something about survival models, because this is, of course, not what the actual lecture is about. Right, I would say where my cliche of demographic historians loving survival models comes from is that I think it's basically just so often the appropriate model for what we call a modern data set in demographic history. I would say that's basically where you're able to follow individuals over time. So in the Dutch context, of course, the historical sample of the Netherlands is a very good example. I'm not going to go into details why it's very appropriate, but it very often would be. But still, to sell the OLS model, right, I think it is worth considering for a few reasons, right? Right, sometimes just often your data might not be suited for this sort of model, right? So say, for example, you have data on lots of municipalities. Maybe you even follow those municipalities over time, and you just have crude death rates for these municipalities. This can potentially answer lots of interesting questions. But yeah, this is a context where OLS will very often be the more appropriate model. And as I mentioned, the ability to tap into those causal inference models. Okay, so let's look at some of the absolute basics of the OLS model. Okay, and we'll have a few equations. Generally, they'll be relatively simple. They're mainly there to sort of clear up terminology as you see them in the paper, right? And the absolute basic population model for regression model just basically looks like this, right? We have a y variable, which we either call the dependent, the outcome, or the response variable. We have an independent variable, which is the x here, which could also be called the predictor variable. And we have an intercept, here that's alpha, a slope parameter, beta, and the little Greek e epsilon here, the error term. And basically the idea is that this is the deterministic part of the model, and the error term captures the non-deterministic part, the part that's not captured by these by the deterministic part of the model. Okay. We're going to look at way more, but already I'm going to say something about how these models are estimated. By the way, one thing I will do in just a bit, which is probably very ill-advised, but I'm going to do it anyway, is I'll be just sharing my R setup to show how some of these things are estimated, rather than, I don't like fiddling around stuffing code in slides. It's a bit, it ends up being slightly more work. So I will sort of be live showing things. So let's hope that goes well. But here I did stuff in some code in the screen to sort of show what happens, right? So an OLS model in R, and here it's absolute base R, so you don't need to install a single thing, is done with the LM command. LM, I'm pretty sure, stands for linear model. So that's doing something here. We're using a data set which is built in. So again, we don't even need to download data today. It's the Swiss data, which comes from the Princeton Fertility Project. And we use formula notation, right? So we're basically here saying we want fertility to be our dependent variable, and we model it as a function of agriculture. And so if you combine it all together, it looks like this. And in R, I tend to think it's always a good idea to assign things. So we assign it, and my habit is to assign it to something called M, and then overwrite that a few lines later, which is a bad habit. All right. One more thing before we return to some of the mechanics of the OLS model is about the alternative for LM. I will actually be using at quite a few places in this lecture. Right. So LM, I think, is an absolutely perfectly fine command. Right. It will just give you completely correct OLS estimates. Right. This is tried and tested. There should be a little D here, by the way, but sorry about that. Yeah, so it does the job. There's lots of extensions written for it, so it's perfectly fine. But like I said, I will be using that fixest library pretty extensively. There's two reasons for that. One is it's very useful when you're estimating something called fixed effects models, which I think by the end of this lecture will become clear is something you will want to estimate very often. Here's another typo, by the way. It's not a good showing on the typo department. So that's one thing, right? Fixed effects models. The other big thing is that if you're trying to write papers sort of for the same audience as I do, which I would qualify as sort of the typical GEH paper, where GEH is the Journal of Economic History, but basically that sort of means all economic and many social history journals. There's just a whole bunch of things, sort of tests and corrections to the model you might want to do. If you want to do that in LM, you need to use lots of external libraries. So, for example, you might end up using, well, 3 of these 4 libraries. Car is not used that often anymore. I think it's quite outdated by now. But sandwich, LM test, and TextRec are very important extensions there, and it's a bit fiddly. Just in fixest, everything is in one nice place. Everything's fast. Everything's efficient. It gives me anyway a very nice workflow. So I wanted to demonstrate that as well, because I tend to think that nice tools make a method nice to use as well. Okay. And like I said, we'll be live coding some of these things in a bit, so you can see it slightly more interactively, but just to show it how the core of this works, right? I'm also assuming you're vaguely familiar with R syntax, right? But if you have a question, don't hesitate to ask. But the nice thing is that the core syntax of this fixest library is actually the same as just LM, so it's sort of a plug-in replacement if you want to. We just need to change two things. One is we need to load this fixest library. If you haven't got it installed yet, you should install it as well, right? That's how R works. And we replace this LM command with this fails, fixed effect OLS command. And I think it's a nice habit to sort of say what library your commands come from, but I'll also admit that after about 30 lines of R, I get a bit lazy and I start skipping it. But this sort of looks, it's kind of documentation in your code, so it's a good habit. You should find, by the way, that if you estimate this and this, the estimates will be completely identical. Okay. I see that this is actually a moment where it's useful to have the estimates on screen. So let me give that a try. So I think you should now be able to see my text editor, right? I'll make it one bigger, two bigger, so we can actually see what's going on. Right, and I think, sorry, colleague walking in to say hi. And then sort of noticing as I was up to something. By the way, please don't look at all my minimized things. This is terrible. All right. So I'm just quickly going to get those results we had on screen just now, right? So I will just be loading that fixest library. But we will just, first of all, let's call it M, and that's M, fertility, and then we did agriculture, right? We're dealing with a very exciting question here, right? Is fertility higher in rural areas? And of course, the answer is going to be yes, right? So again, if you're familiar with R, it will not be a surprise that once you've estimated something, you can just sort of send it to the console by just printing the object you've created. And then you basically just get your coefficients. But we want slightly more information, right? We also want lots of details for later, and then you do summary M. For the fixest library, it's all slightly different, right? So we have this fails command, right? And other than that, it is just the same as the old one. The nice thing is we can also here, you can still do summary of this fixest thing, and then it looks a lot like the old one, right? It's very nice to see that just the results are the same, right? That's it's always a bit worrying if your computer changes your mind between running what should basically be the same command twice. Nice thing about the fixest library is that you also get, I think, slightly nicer formatted tables, right? This is sort of as you'll see them in the publications as well, and they'll be very useful later on. For now, though, notice two important numbers here, namely our constant and our coefficient estimate of beta. So the constant is 60.3 and the coefficient estimate is 0.19. Okay, so if we go back to our slides just now, right? These things, like I said, doing these things live is never a great idea, but we'll get back on track in a bit. Right, so this is the constant, right? That's alpha. And this is our slope coefficient. Here it's beta on the variable agriculture, 0.19. Okay. And what we really want to do is sort of see, I think it's useful especially if you're reading these sort of economic history and economists journals, right? They sort of skip all the graphs and go straight to the tables. So you end up with lots of regression tables, which look like this, or an example I'll give in just a bit as well. But I do think it's just useful to be reminded what an OLS model just actually does in its core, right? And so the intercept, the 60.3 we had, is right here. It's just where the regression line, because that's of course what it's doing, it's where it meets the y-axis. So that's the 60.3, and the 0.19 is basically the slope of the line, right? If we go back here and you sort of remove the error term and the little indexes with the y, and you sort of change the Greek letters by normal Latin letters, right? I don't want to dunk on the Greeks, but then it's sort of like high school math again, right? It's a plus b times x, y is a times b plus a plus b times x, and it's describing a straight line, right? And that's essentially what a regression model is doing. It's finding this line, and this is basically just where it meets the y-axis. That's often called the intercept or the constant, and the beta is the slope. I've multiplied, by the way, this number here by 10 because otherwise it would be really, really, really tiny, and that doesn't work. But the nice thing about a linear model is that you can just multiply things by 10, and it just all works. All right. So yeah, the nice thing about before we get to some more details about what, by the way, the actual OLS bit, because I haven't even said what OLS actually means, but we'll get to that in just a minute. The really nice thing, of course, about a regression model like this is that the interpretation of the output is something very close to what you would actually want to have in a paper, right? So if we briefly go back to what we have here, these are all my other slide collections, right? What this model is basically telling us, because that's basically what this line is telling us. I hope you don't get dizzy from all my sliding back and forth. It's basically saying that if we increase agriculture, so the percentage of the population who works in agriculture, by the way, how this is measured in this built-in data set, if we increase that by 1, the fertility is predicted to increase by whatever number we got for that beta. So here it's basically saying a 1 percentage point increase in the population who works in agriculture predicts a 0.2 increase in fertility. And I think this is one of those standardized fertility rates, right? And that's exactly, I think, the sort of thing you might want to say in a paper, which is, I think, one of the reasons this is such an incredibly popular method in all of social sciences. And it is, of course, slightly different than the odds ratio you would find in many the odd ratio interpretations you get in a lot of demographic history papers. Okay, like I said, we have to skip a lot. Usually we would say a lot more and practice a lot with getting these interpretations right. I also want to show another concept, which is the residuals, right? So like I said, we try and split the data, if you will, in a deterministic part, which is this line described by nothing but the intercept and the slope parameter. And you, of course, have the bit you don't explain with this simple line, which are these distances to the regression line, which are called the residuals. And here's a moment where I'm going to give myself like a 10-second talking break by asking you how you would determine what the intercept and the slope of this line would be. Of course, what I'm hoping is that someone will volunteer to answer the question. At least have a go at it. But in principle, I'm also happy if we just take like 5 or 10 seconds and think how we might do that. Right. So what typically I borrowed these two slides from a class I teach in another context, which is basically what students very quickly say is, well, you want to make the distance between the line and the residuals as small as possible. Right. And of course, I would then very quickly point out that some of them are negatives. So what are you going to do about that? Well, and then they usually say, well, what if we take the absolute number? And then I say, that's a great idea. But what we actually do is we square these numbers. And that's where, of course, I'm going to explain what OLS means. It's you minimize the least squares. And why you do that rather than keeping the, for example, minimizing the absolute distance, sort of the absolute sum of the residuals. That's lots of technical stuff. So we can't really get into that now, but this just turns out to have lots and lots of nice properties. But basically, right, you square these distances and then they become little squares, and you try and make that number, the sum of squares, as small as possible. Okay. To say something, so typically also if you would follow statistics course, which deals with a lot of OLS, you would end up talking about the assumptions you need for OLS to be a sort of optimal estimator, technically the sort of the best linear unbiased estimator. But you want it to have two things, namely you want it to be unbiased so that the expected value that should have a little hat on it. That's very bad. The expected value of beta had to equal the true population parameter. And you also want the variance of beta, so for statistical inference, to be as low as possible. So, yeah. So that there are these 6 assumptions you need for that. This is, okay, I'm not going to go through these in detail. In fact, I'm going to skip all but 2 of them. Because many of them are actually, this, for example, is only interesting if you're estimating time series models. These 2 are usually just dealt with by the software, so you don't have to worry about this. But I do think there are 2 important ones to keep in mind. One is that the model you're trying to estimate is linear in its parameters, right? Which basically means you can describe it by that sort of formula we had a few slides back, namely a constant plus a constant times a variable plus a constant times a variable. Basically, it should be constructed of plus and multiplication signs, right? There's slightly more to it than that, but in a very simplified way, you could think about it like that. But that is important, that if sort of the process you're thinking about is very poorly captured by talking about it in linear terms, then it could, of course, be that OLS can't help you, or actually more likely, you sort of need to apply the necessary variable transformations to actually get what you want. But it is important, and usually this one isn't really thought about all that much, but I think that's a bit of a shame. All right, the big important one that's usually hammered on in intro statistics classes, there should be no correlation between the independent variable, sorry for all the back and forth, that's this one, and the error term, this one. Okay, what that basically comes down to is that there should be no omitted variables. So variables which impact the outcome variable and which are correlated with one of the independent variables. Then your estimates will be biased. And that's really not what you want. And that sort of brings us to the causal inference terrain. Okay, maybe very briefly, should I be aiming for a slight break between me and Mayra, so that we sort of wrap up at 10:02 or 5:02, or should I go on until 3 at the dot?
Maybe a short break, but not really break, but maybe time for questions. Yeah, so
Right,
if you
right,
finish
right,
a bit
right.
earlier,
Okay,
I think
okay,
it's good
okay,
that people will have time for questions. Yeah, yeah.
No, good point, good point, good point. Okay. Okay, so that means I'm going to go in sort of slightly higher speed through the statistical inference bit, not because it's not important, but because there's just so much to it it was never my intention to cover it completely anyway, right? But to be very brief, right? So we get an estimate of beta, which we would usually call beta hat, which is the slope parameter that we're usually interested in. And in a frequentist statistics framework, right, this estimate comes from a population and would have, well, a sampling distribution and, well, then you do the typical things of statistical inference, like do a significance test or calculate a confidence interval. Okay, so to skip the sort of the actual mechanics of doing a hypothesis test on a regression model, right? Like to cut a lot of corners, typically we just want our p-values to be smaller than some agreed on threshold, usually 5 or 1%. But I briefly want to mention no, okay, so I've started now, so I'll finish it. We have this formula here for calculating the standard error of beta, which would be the input for confidence intervals, p-values, t-statistics, etc. But what I want to highlight is, so this is basically just a formula of how it's calculated in the bivariate regression case. There's also a multivariate case, which is of course slightly more complicated. But it is, they share a core of how it's calculated, and they sort of hint at what you need from your data or your research design to get statistical power, which I will here sort of with some disregard of actual formalities here define that if there is a true effect in the population, right, so the actual true value of beta in the population is not zero or not extremely close to zero, but it's a real and meaningful number, that your data can actually recover this, right? Which would basically mean that you have enough precision on your estimates. Basically, that means in this formula, you want the denominator to be as small as possible, because then the standard errors will be smaller, and that sort of has consequences all down the road. Well, that comes down to a couple of numbers. One is you have this 1 minus rk squared term here, where this thing, rk squared, is basically the r squared. Sorry, I sort of forgot to superscript this little 2. Comes from an auxiliary regression of your independent variable of interest, xk, again, skip the underscore there, sorry about that, on all the other variables in your regression. And of course, the higher this number is, the worse it is. Basically, this means if your independent variable of interest is highly correlated with all your other variables, or one of your other variables, this will hurt your precision and your statistical power of your design. So this basically comes down to, right, if your independent variable of interest is share of the population working in industry, it's probably not a good move to include share of population working in agriculture, because of course they will be mechanically highly correlated, and doesn't contain a lot of information, will just hurt you. Okay, the other one is here something called the total sum of squares, which is basically those little lines turned into squares. Basically, right, if you turn these into squares and add them all up, what number comes out of that? Well, the bigger it is, the smaller the standard error on beta will be, and the more statistical power you will have. Basically, there's two things coming in here, right? That's basically the variance in your independent variable x. So you want that to have, if it doesn't vary a lot, of course, it'll be very difficult to measure its effect on the outcome. So it immediately intuitively feels true. And of course, the other bit is the total sum of squares. So of course, the more data you have, the better, right? In quantitative research, it does tend to really be that more is more. So yeah, so that's also one of the nice things here. This was a bit of a detour, maybe. This is also one of the sort of nice things, because the OLS model is, especially in the bivariate case, relatively simple. it means that you can sort of really learn things from the basic formulas of how it's constructed, right? And the more complicated your models get, the harder it is to keep track of what's going on. But here, right, you could just find a couple of YouTube videos which talk through these sort of things, and my guess would be that most of you could just follow along with what's going on there. Okay. Bum, bum, bum. We've already done that, so that's excellent. I'm catching up on some of my work. But let's look a bit at what the what the output of a regression model looks like, right? I'd already mentioned that 60 here is just where the regression line meets the y-axis, wherever you're basically where x agriculture is 0. That this is the slope parameter. This is that standard error I've just talked about, which in turn are used to construct two things of interest, right? We have our t-statistic, and if it were still, let's say, the 1980s, you could sort of pick up your statistic book and go to the appendix, where there would be a big table with the critical values of the t-distribution, and it would tell you whether you could reject your null hypothesis of no effect at some level of confidence. Of course, nowadays the computer just calculates the appropriate p-value for us. So that basically tells this is what you would typically do your statistical inference on, right? So in this case, the p-value is 0.01, which is smaller than the conventional threshold of 0.05. But of course, this threshold is just a convention. You could also say it's 0.01, and then you would not meet this threshold. But if the case were that it was 0.05, we could reject the null, accept the alternative hypothesis, and then you could basically report on this interpretation that a 1 percentage point in agriculture, blah, 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 sorry about that, but otherwise I repeat myself so often, would predict a 0.2 higher standardized fertility rate. Right, so those are some of the key things. This is that estimate column. These are the standard errors, the t-statistics, and the p-values, where typically I would say sort of the first and the fourth column is often what you would be looking at. You get a few more things, right? So you get your R squared, of course, and there's also lots of other things like F statistics on the model, but frankly, you don't really end up using those all that often. Okay, maybe to just briefly show again how the fixest library is slightly different, right? We get a lot less information than we do in this one, right? We're told what the dependent variable and the independent variables are. Is that still the same? The coefficients are of course the same. We get the standard errors. I could ask for other things. I'd have to look up how that goes, but this is the default option. This is also what you'll find to be the default option in many journals. And then the actual p-values are communicated through these stars, right? Where 3 stars typically means that you meet the 0.1 percentage threshold. Oh, there we go. Yes, there's the actual answer. And that 1 star would be the 0.05 threshold. It also tells us how the standard errors have been estimated. We'll come to that in such a bit. And also nice things, right? We get the actual observations, which I think is easier to understand than the degrees of freedom, even though technically this is more interesting. And here's R squared again, right? It is this core of the information is the same. It's just slightly better formatted. And we'll see some of the formatting options in a bit as well. Okay. I'm going to skip over some things because otherwise we spend way too much time on that. I'm going to sort of briefly summarize something like 4 or 5 slides in just 2 sentences, right? So far I've been talking about the bivariate regression. Of course, OLS also allows you to have multiple independent variables, and then it becomes multiple regression. And the nice thing is that the slope variable is then interpreted, keeping all other variables constant. Okay, I had some slides sort of trying to get at the intuition of that. All right. Okay, I will just quickly demonstrate what I tried to show here, right? Which is this question here about comparing models to see what happens if you regress something on multiple variables, right? So we can regress. This is wrong. See if I got this right. Yes, I do. All right. Okay, so we'll use these numbers later on, so that's why I quickly wanted to get them on the screen. But the nice thing is also that this sort of shows you that special e-table power is that you can now also quickly and easily compare models right next to each other, right? And what's important to highlight here is that as we include other variables, the coefficient on our original variable of interest changes, right? The idea was here that we would regress infant mortality, fertility on infant mortality. The idea being that if infant mortality is high, fertility might be higher to compensate for it. And here we sort of address education as a confounding variable in that. But we'll look at that in a bit. All right, so look at what's going on here, right? So we once had the interpretation that a 1 unit increase in infant mortality predicts a 1.7, that should be 1.8 increase in standardized fertility, whereas a 1 unit increase in infant mortality in the second model predicts a 1.5 point increase in standardized fertility, keeping education constant. Okay. I want to talk about this model from a sort of a causal perspective, right? So if we look at this simple model where we regress fertility and infant mortality, the argument here would be why I chose these models, and all the examples here will be somewhat contrived, right? They're just meant for exposition, not to be an extensive discussion of the actual topic, is that you could argue that education is an omitted variable, right? Remember that I said that was always the big thing people were worried about in the assumptions underlying an OLS model. So the idea basically is that education could impact fertility. Can think of this in a couple of ways, right? Could be that how you actually control fertility requires some knowledge. So if you had some school and you can read and write, that could help in obtaining this information. Or alternatively, you could also say, what if some of that education is actually education of women? I believe the context here is 1890 Switzerland, so there's probably some of the differences between the various districts of Switzerland might be down to education levels. And if women have higher fertility, if women are more educated, it's more interesting for them to be on the labor market. They can probably earn a bit more money. Typically, what we would expect is that they will start having children later, so fertility would be lower. Education will also be related with infant mortality, right? So again, sort of knowledge to keep your kids alive is something which could be spread through education, or you could argue that education sort of means you can earn more, which makes it easier to keep your kids alive. So that's a classic case of omitted variable bias. So we can include it, and indeed we see that the estimate on our variable of interest, in this case, infant mortality, changes. So that's sort of one of the interesting things about multiple regression this way, right? So if in a sort of make-believe situation where education was the only confounding variable we were worried about, we would have corrected our original biased estimate into sort of an unbiased causal estimate. Okay, but so it's you can probably see this is basically just what I told you just a half minute ago. What I hope you can see is that it's can be quite difficult to sort of reason about these changes in the coefficients, and it's hard to know what all the variables are you should include as well, especially once you realize that a thing like a bad control exists anyway. Right, usually we want to be a bit more parsimonious, right? So we want to be as few variables as possible to get where we need to be, and just basically throwing all your variables in the regression is well very much frowned upon in the field. So yeah, what you typically end up doing is slowly building these models, sort of one variable at a time. And I'm sort of showing you the results of a paper of myself with two colleagues, so Pim de Zwart and Daniel Gallardo in Wageningen, who well, we worked on this together, and this is really the sort of the stepwise building of a model where we're interested in how the cultivation system, in particular the forced labor rates in the cultivation system, on colonial Java impacts crude death rates, right? And the exact story and why that is so interesting to know is sort of not what we're looking at here. The basic point is building that model slowly, one step at a time, to see what's going on. And again, what's kind of interesting to show here, and I'll do it sort of with the things I made earlier, is to kind of see how this fixest library can be used to get these estimates very quickly, right? So if we do it like this, it's being a bit difficult about the formatting, but you can sort of see how you can relatively easily build this model and sort of compare the output. The nice thing is you can also output this straight up for your papers. Okay. Like I said, I have sort of misjudged how long I would talk about everything else by about 10 minutes. So I'm very sorry about that. I was hoping it would be like 1:45 now, and it's actually 7:02, so that's not so great of me. But like I said, I was talking about these omitted variables and the causal inference issue, and also one thing I skipped over was sort of a very make-believe example of very obvious omitted variable bias like this. But what I hope you do sort of immediately sense, also just from being active in a field like demographic history, is that being able to give a causal interpretation to your statistical models would be nice. But there is always this lurking issue of omitted variable bias, or maybe reverse causality. And yeah, there's a couple of solutions out there. And of course, all these solutions come with a big asterisk that all sorts of assumptions need to be met. And I just want to list a few of them, and what I'll probably do is try and show just two of these very briefly, very superficially. Right, one thing you can do is, if you sort of go on, follow along with that, you're able to include control variables. A way of looking at it is you could have a complete model, not a completely model, that's sort of nonsense, complete model of the data generating process, including all the control variables which are relevant in the right functional form. You can probably sense that this is quite difficult. That said, right, just having an estimate of a relationship controlling for a few important variables can already be a very valuable step. But you can see that a complete convincing causal interpretation just from using control variables can be hard. So there's sort of a suite of tricks which are very popular in sort of my neck of the woods. all extensions of the OLS model, which can really help here. So there's something called regression discontinuity designs, difference in differences, and instrumental variables. Panel methods are there as well, right? And it's a very exciting sort of suitcase of methods, because it basically means it is probably possible to get causal statements from observational data, right? And as historians, we are never going to do randomized experiments, so this is the best we're ever going to do. But it's also dangerous, right? So it's easy to misapply them. And if you sort of look at the empirical papers applying these sorts of methods, there are lots of appendices with all sorts of technical checks. So typically it is really a literature to catch up on. Okay. So in the OLS context, I'm going to talk briefly about those panel and fixed effects models now. You have something called, if you have like nested data, so think like following individuals over time, or individuals who live in municipalities, or maybe they're municipalities grouped in provinces, these sorts of things. Typically in an OLS context, you use two things: fixed effects and clustered standard errors. The last thing is something I'll not say much more about than other that they're a trick to deal with within group correlation, right? So if you follow an individual over time and say, for example, you're looking at their health, if they're unhealthy at TS1, they're probably also going to be unhealthy, or the chance of them being unhealthy at TS2 is higher than it is for other individuals, right? So you get this within group correlation where clustered standard errors should help. There's also something called fixed effects, which are basically dummy variables for the nesting group. So say, for example, again, we're following individuals over time. You would include a separate dummy for every individual. Technically, you actually do something else. You demean the data, but the numbers that come out will be equivalent. And if you go back to that table from the cultivation system regression, right, you see that we have these fixed effects here. They're basically always there. These are the residency fixed effects. And we also have year fixed effects at some point, right? And we can also see, they're recreated here, how you can make those with those fails library, the fixest library, right? At some point, I basically just add this horizontal bar and add my fixed effects, and then they just very neatly get included. The point about the sort of standard errors, these are also very easily specified in the fixest library, right? You can specify the VCOF for the variance covariance matrix. You can specify that. Sort of really stuff we can't get into is we use something called Driscoll-Cry standard errors, and they're basically just available. So is a whole bunch of other ones. Okay, very briefly, because I do want to wrap this up in 1 minute now, which is a bit of a shame, but otherwise, I'm getting into Maida's time, which would be very inconsiderate behavior of me. There's something called difference in differences. It's extremely popular. I actually prepped a little demonstration of this on the basis of the historical database of Dutch municipalities, but I think I'll just add them to the slide deck in about 4 or 5 slides for you to look at. But basically what it comes down to is if you've units which you can follow over time, and if you're willing to assume, or even better, can see in the data that you expect these groups to develop on parallel trends, and one group experiences what that would be called the treatment, right? That's really sort of taking the randomized controlled trial terminology to the thing. But if one of them experiences an event which others don't, the change in trends and the resulting difference can be given a causal estimate. And you can probably see that the data demands for this method are not that high, right? You need a bunch of individuals, municipalities, or countries, or whichever, which you can follow over time, and some part experiences what you're interested in, and the others don't. So that could, for example, be cities which get a hospital, whereas others don't, right? And you can compare them very efficiently in this way. Okay, very famous example is the literature on the Mariel boat lift, very much worth looking into. It is now actually 3 o'clock. So I will actually just stop talking, and sorry for talking too much on points I shouldn't have talked about, so I would have been done on time. But I hope there was some stuff of interest regardless.
Thank you very much, Auke, and sorry I wasn't here at the very beginning, and welcome.
No. It was explained.
Oh, great. Thank you very much. And yes, thank you. I think it is your presentation was very excited for me, and I learned, because as an economist, I really like to listen anything about OLS.
Right. Oh, my assumption that everybody was sort of a demographer, demographic historian was off.
Oh my.
I will just expand the slides with the historical database, the Dutch municipality example, before I upload the slides. It sort of demos what's going on. So I do think that's kind of interesting. Yes.
Great. Whenever you are ready to send it to me, I can upload the page and let you know, and the others as well.
All right.